Welcome to all. My name is Saurabh Mandal, Assistant Professor of Applied Electronics and Instrumentation Engineering Department, Volta Institute of Technology. Today I am going to discuss one very important topic of digital electronic circuits, which is universal logic gates. Before I discuss universal logic gates, first we have to know what is logic gates, what is the utilities of universal logic gates based on logic gates, and how logic gates is very much useful to designing different type of digital circuits also. So a logic gate is an active electronic component that uses one or more inputs to produce an output based on the Boolean algebra each gate is designed to perform. What exactly it means? It means that a logic gate is an active component which is basically designed to perform a specific operation maintaining the logic of Boolean algebra. Different logic gates are performing different logical operations maintaining the Boolean algebra, and already we have known that whenever we are talking to digital electronics, the first thing came to our mind, that is the binary number, and in binary number only 0 and 1 is there. So logic gates are such type of electronic components where whenever we are providing any input combination in terms of 0 and 1, it will provide the output also either in 0 value or 1 value based on the logic of that particular logic gates, and definitely maintaining the Boolean algebra. So many types of logic gates are available in market, such as NAND logic gate, NOR logic gate, NOT logic gate, AND logic gate, OR logic gate, XOR logic gate, XNOR logic gate, etc. Different logic gates has different function, such as if I consider NOT logic gate, the function of NOT logic gate is to complement the input value. That means if we provide 1 as input, then it will provide 0 as output. Same, if we provide 0 as input, it will provide 1 as output. Just the opposite of input value. Whenever talking to all logic gate, the operation of all logic gate is that if we have 2 input all logic gate, then any value of these 2 input is 1, the output will become 1. But if both the input value is 0, then only the output will be 0. That means if we have 2 input OR gate, then for 0, the output will be 0. For 1, the output will be 1. For 1, the output will be 1. For 1, the output will be 1. For that case of AND logic gate, if we have 2 input AND logic gate, then whenever both the inputs are 1, then only the output will be 1. All other case, the output will be 0. That means for 1 input, the output will be 1. For 0, the output will be 0. For 1, the output will be 0. For 1, the output will be 0. For that case of NAND logic gate, it is just the opposite of AND logic gate operation. That means what output we get from AND logic gate operation, we get just opposite for that case of NAND logic gate operation. That means if we have one 2-input NAND logic gate, then for 0 0 the output will be 1. For 0 1 the output will be 1. For 1 0 the output will be 1. For 1 1 the output will be 0. Just the opposite of AND logic gate. If we have OR logic gate, already I told what will be the truth table of all logic gate. Now, if we have non-logic gate, then the output expression of non-logic gate is just the opposite of all logic gate. So, if we have one 2-input non-logic gate, then the output of 2-input non-logic gate will be for 0 0 the output will be 1. For 0 1 the output will be 0. For 1 0 the output will be 0. For 1 1 the output will be 0. Just the opposite of all logic gate. For the case of XOR logic gate, the output will be 0 when both the input is same, and the output will be 1 when both the inputs are not same. That means if we have one 2-input XOR logic gate, then for 0 0 and 1 1 combination, the output will be 0, and for 0 1 and 1 0 combination, the output will be 1. And for that case of XNOR logic gate, it is just the opposite of XOR logic gate. So, if we have a 2-input XNOR logic gate, then for that case of 0 0 and 1 1, the output will be 1, and for that case of 0 1 and 1 0, the output will be 0. Just the opposite of XOR logic gate operation. So, non-logic gate operation is just opposite of all logic gate operation. NAND logic gate operation is just opposite of AND logic gate operation. XNOR logic gate operation is just opposite of XOR logic gate operation. Now, among all the logic gates, NAND logic gate and non-logic gate are known as universal logic gate. Why? Because with the help of these two logic gates, we can implement any type of Boolean function. Or we can say, with the help of these two logic gates, we can design any other type of logic gates. Though we can design any other type of logic gates, or we can implement any type of Boolean function, these two logic gates, that means non-logic gate and non-logic gate, are known as universal logic gates. So, what are universal gates? The universal gates are the logic gates that are versatile in that they can be programmed to execute any Boolean function. Already I discussed. Universal logic gates can implement any type of Boolean function. The most popular types among them are NAND and non-logic gates. Simply we can say any other logic gates we can design only with the help of NAND and non-logic gates. So any type of logic gates we can design with the help of NAND and non-logic gates. So whenever we can design any other type of logic gates with the help of NAND and non-logic gates, that indicated that we can implement any type of Boolean function with the help of NAND and non-logic gates. Now come to that particular portion by which we can understand how NAND and non-logic gates is used to design any other type of logic gate. So first I am discussing with the help of NAND logic gates. So with the help of NAND logic gates, we will see one by one how to design NOT logic gate, OR logic gate, AND logic gate, XOR logic gate, XNOR logic gate. That means all the types of other logic gates. First, we'll see the symbolic representation of NAND logic gate and non-logic gate and their corresponding truth table. So, this is the symbolic representation of NAND logic gate. So, we can see in this picture, this is the symbolic representation of NAND logic gate and the truth table of that NAND logic gate. Already I discussed that the operation of NAND logic gate is just the opposite of the operation of AND logic gate. So, the truth table of NAND logic gate is, if it is 2 input NAND logic gate, then for 00 it is 1, for 01 it is 1, for 10 it is 1, for 11 it is 0. And the Boolean expression of NAND logic gate is y equals to a dot b whole bar. For the case of non-logic gate, this is the symbolic representation of non-logic gate and the Boolean expression of non-logic gate is a plus b whole bar. For that case of NAND logic gate, it is a dot b whole bar. For that case of non-logic gate, it is a plus b whole bar. And the truth table for non-logic gate, if it is 2 input non-logic gate, then the truth table of non-logic gate is, for 00 it is 1, for 01 it is 0, for 10 it is 0, for 11 it is 0. Now, first we'll see how to design NOT logic gate with the help of NAND logic gate. So, this is the circuit design pattern of NOT logic gate from NAND logic gate. Here we can see I have used one NAND logic gate and the inputs of that particular NAND logic gate are sorted. So, whenever we can sort it both the inputs of NAND logic gate, it will become NOT logic gate. Why? Because the Boolean expression of NAND logic gate already I told, that is a dot b whole bar. So, whenever we are sorting these two inputs, then a will be equals to b. So, in the position of b, we can write a. So, the Boolean expression will be a dot a whole bar, and according to Boolean law, a dot a, that is equals to a. So, a dot b whole bar, that means a dot a whole bar, that means a bar. So, if the input is a, the output will be a bar, which is nothing but the Boolean expression of NOT logic gate. So, by sorting two inputs of NAND logic gate, we can simply design NOT logic gates with the help of NAND logic gate. Next, NAND to AND. Now, what exactly the difference between NAND and AND? The logical operation of AND logic gate operation is just opposite of NAND logic gate operation. So, whenever we want to design AND logic gate with the help of NAND logic gate, then simply we have to add one NOT logic gate with this NAND logic gate to get AND logic gate operation, because complemented of NAND logic gate operation is nothing but the AND logic gate operation. So, if we add one NOT logic gate along with NAND logic gate, it will become an AND logic gate. So, that is indicated in this circuit. So, here the first logic gate is simply NAND logic gate, and the second NAND logic gate is nothing but representing the NOT logic gate. So, the output of first NAND logic gate is a dot b whole bar, and the output of second NAND logic gate is A dot B whole bar, again another whole bar. That means A dot B double bar. And whenever it is A dot B double bar, then according to Boolean law, it will be A dot B, which is nothing but the Boolean expression of AND logic. So ultimately, with the help of adding one additional NAND logic gate where two inputs are sorted, we can easily design AND logic gate from NAND logic gate. Now, next NAND to OR. So whenever we have to design all logic gate with the help of NAND logic gate, then the circuit design will be look like this. Here, three NAND logic gates have been used. Now, these three NAND logic gates are using to design a all logic gate. Now, among these three NAND logic gates, first two NAND logic gates are using to get the complemented output. So, the output of first NAND logic gate is A bar and the output of second NAND logic gate is B bar. And these two output is acting as input of the third NAND logic gate. So, according to the Boolean expression of NAND logic gate, the third NAND logic gate output will be A bar dot B bar whole bar. Now, if we apply De Morgan's theorem, then it will be A double bar plus B double bar, because according to De Morgan's theorem, A dot B whole bar, that is equals to A bar plus B bar. So, in that sense, A bar dot B bar whole bar, that will be A double bar plus B double bar, and A double bar that is equals to A and B double bar that is equals to B. So ultimately it will become A plus B, which is nothing but the Boolean expression of all logic gate. So accordingly we can design all logic gate from NAND logic gate. Next, NAND to NOR. So whenever we have to design NAND to NOR, then what we will do? We'll first design NAND to OR, and after that we'll add one additional NAND logic gate which will be acting as NOT logic gate. So the circuit is accordingly, the first three NAND logic gate is used for design to all logic gate, and the fourth NAND logic gate is used to design that NOR logic gate. That means complement of OR, though the fourth NAND logic gate is acting as NOT logic gate. So OR plus NOT ultimately NOR. So ultimately we are getting non-logic gate operation with the help of this type of circuit. Next, NAND to XOR. Whenever we are designing NAND to XOR, then the circuit will be look like this. We are using 4 NAND logic gate to design NAND to XOR. Now, the circuit will be look like this. So, according to that particular circuit, the output of first NAND logic gate will be A dot B whole bar. The output of second logic gate will be A dot B whole bar total bar, and the third NAND logic gate B dot A dot B whole bar total bar. Because just if we see for second NAND logic gate, one input is A and another input is the output of first NAND logic gate, which is A dot B whole bar. So accordingly, the second NAND logic gate and the third NAND logic gate will provide the output A dot B whole bar total bar and B dot A dot B whole bar total bar. Now, fourth NAND logic gate, the output will be just, we'll see the output of second NAND logic gate and the third NAND logic gate are acting as input of fourth NAND logic gate. So, in that sense, the output of fourth NAND logic gate will be y equals to a dot b whole bar, b dot a dot b whole bar, again bar and the total bar. Now, if we simplify this expression with the help of De Morgan's theorem, it will provide a dot b whole bar plus b dot a dot b whole bar, that is equals to a into a bar plus b bar plus b into a bar plus b bar, which is nothing but a dot a bar plus a dot b bar plus a bar dot b plus b dot b bar. And we already know that one, a plus a bar, that is equals to 1, but a dot a bar, that is equals to 0. Same thing, b plus b bar, that is equals to 1, but b dot b bar, that is equals to 0. So, accordingly, a dot a bar, that will be 0 and b dot b bar, that will be 0 according to Boolean C. So, the remaining a dot b bar and a bar dot b will be present, and finally the expression will get a dot b bar plus a bar dot b, which is nothing but the Boolean expression of XOR logic gate. Next, the last portion of NAND logic gate circuit design is NAND to XNOR, and the circuit will be look like this. Now, whenever we have to design NAND to XNOR, what we'll do? We'll first design NAND to XOR, and after that we'll add one more NAND logic gate which will be acting as NOT logic gate operation, because the complemented of XOR logic gate is nothing but XNOR logic gate. So, if we add one more NOT logic gate with XOR, it will become XNOR, and accordingly the circuit is this. So, here the fifth logic gate is acting as NOT logic gate, and accordingly we will get the output A XOR B whole bar, where A XOR B is nothing but the Boolean expression of XOR logic gate. So, A XOR B whole bar is nothing but the Boolean expression of XNOR logic gate, and the circuit it look like this. So, with the help of, by using 5 NAND logic gate, we can design XNOR logic gate operation from NAND logic gate. That's it for today. In my next session, I will try to discuss the different type of circuit design from non-logic gate. Thank you very much.